Welcome to this online meeting on the sixth major IPCC science report and its implications, hosted by the Royal Meteorological Society. I am David Warrilow, Vice Chair of the Society, and this meeting follows other meetings we have hosted which have considered previous IPCC reports, such as the 1.5C report and the reports on the oceans and land use. This IPCC report marks a landmark for the IPCC in that it was finalised and approved in a virtual process, a truly remarkable achievement. And this is an opportunity to refresh our minds on the main findings of the report. And this morning we have 6 speakers, all contributing authors, and my thanks to them for being willing to take part. This afternoon, we will have the opportunity to consider what its findings mean for action on climate change through mitigation and adaptation responses. My thanks also go to our 10 panelists and to our chairs, Tim Osborne and Richard Black. There will be some opportunity for Q&A during the morning session and wider discussion during the panel sessions this afternoon. We are expecting over 500 participants, so we ask that you put your questions and comments on the chat facility. Finally, the meeting will be recorded and posted on YouTube by tomorrow. So I now turn to Tim Osborne to chair this morning's session. He's the director of the University of East Anglia's Climatic Research Unit. Tim, over to you.
Thank you, David. It's very nice to see so many of you joining us today. I think it really makes it worthwhile for the speakers to have such a large and interested audience. I think it also demonstrates the importance with which the IPCC's assessments are held. So we've split the pre-lunch talks into 2 blocks. First on the large scale and global scale climate changes, and then second block will be on some of the risks and uncertainties arising from climate change. We're going to have a consolidated Q&A session after each block of 3 talks. So the way this will work is that you'll put your questions in the chat area. So if you could precede the question by the first name of the speaker who you'd like to direct your question to, that will help us. I will endeavour to ask as many of your questions as I can during the Q&A session, but I expect we may not have time to get through them all. It would help me in doing that if you could refrain from using the chat for general chit-chat. So stick to questions, please. So all of our speakers are eminent scientists who deserve lengthy introductions, but I'm only going to give them a short introduction today, so I don't eat into their time for speaking. So I'm sure you'll want to hear from them more than you want to hear from me. But please look at the meeting website if you want to know more about our speakers, because they have a short bio in each case. So there's some instructions on the screen now that just disappeared, which I think covered what I was just saying there about the chat and that the meeting's been recorded. So we're going to move straight on towards our first set of talks. So if you could please start sharing your presentation, Peter. And I'm pleased to introduce Peter Thorne from Maynooth University in Ireland, and originally a PhD student here at UEA. Peter was a coordinating lead author for Chapter 2, and he's going to talk about the observations and causes of climate change. So take it away, Peter.
Okay, so you can see my screen hopefully and see me. So as Tim noted, I was from UEA originally. I'm now at Maynooth University, and I'm going to talk to you about observations and causes. So the very first thing to talk about, well, firstly to note that the text here is text directly lifted from the summary for policymakers of the report. I'm not going to read it all. I'm going to use it as a guide for you, and so that you can use it after the talk. So where else to start but greenhouse gases, the trace gases that are so critical to our climate system. And it is unequivocal that the increases we have seen have been caused by humans, and the changes we have seen are outside of anything we have seen in the ice cores for the last 800,000 years, and for carbon dioxide, for which we have other proxies, for at least 2 million years. So we have fundamentally altered the greenhouse gas concentrations. The changes are much larger than between consecutive ice age or glacial and interglacial cycles over the last 800,000 years. What does that mean in terms of the radiative forcing of the atmosphere? So here the key line is the black line. All of the other lines are the constituents, and the black line is north of 2.5 watts per meter squared. It's actually at 2.7 watts per meter squared. That's the additional top of atmosphere radiative imbalance, effectively, that we have forced upon the atmosphere system. And that's driving fundamentally the change that we see. So, having looked at the change in the constituents and the change in the radiative forcing, the next natural thing to look at is the temperature changes that we have seen. And each of the last 4 decades has been consecutively warmer than any preceding decade. We now stand today at about 1.1 degrees centigrade higher than 1850 to 1900, which is the closest we get to a proxy for pre-industrial. The maps on the left-hand side in this figure show that the rate of warming has increased considerably since the latter part of the 20th century. And warming is much greater over the land than the ocean. So although in the global mean we might be at 1.1 degrees centigrade, actually over land we've already breached 1.5 degrees centigrade. So where people live and where people care about, we're already above the 1.5 degrees. We can look in the long term. This is a figure from the summary for policymakers, or the left-hand side of that figure. The black line on the right-hand side is the direct observations, and the blue and its shading is the reconstructions from a range of methods of global surface temperature. And this now goes back further and with higher fidelity than prior assessments. And it really is the case that the observations are highly, highly unusual in the context of reconstructions. So warming is unprecedented in more than 2,000 years. The rate of warming is huge compared to anything we've seen in that period. We tried, particularly in this assessment report, to ask the question, well, when was it last plausibly like it is today? Now, there are caveats here around the fact that when you go back beyond 2,000 years, you start going to centennial timescale reconstructions. So you start comparing a little bit an apple to an orange. But nevertheless, the warmest period in the current interglacial, about 6,500 years ago, is now assessed to have been between 0.2 and 1 degrees warmer than 1850 to 1900, which means in the most recent decade, we have breached that. The next youngest plausible period in which it could have been as warm as today is the peak of the last interglacial about 125,000 years ago. Why does that matter to us? Well, we fundamentally developed from a hunter-gatherer through an agrarian revolution, through an industrial revolution, through a technological revolution to today in that, if you like, safe operating space of the current interglacial. And we've pushed the climate system outside that. And it's definitely us. We have forced the climate system. You will have seen this type of figure almost undoubtedly before. The green here is simulations with multiple climate models contributing to CMIP6, the couple model into comparison, run with just changes in solar and volcanic outputs. and you just cannot explain the most recent 50 or 60 years with that set of simulations. When you add in the orangey brown, the simulated human influences, the greenhouse gases, the changes in aerosols, atmospheric particulates forced by human activity, suddenly you can explain the observations, the black line. So we really know that it's humans. Humans have contributed effectively all of the warming. And there is very little contribution from natural drivers or internal variability. This is another SPM figure that says effectively the same thing. So on the left-hand side in part A is the observed warming over the period to 2019. And then in the middle is your classical attribution analysis, whereby you've quantified the total human influence and it matches the observations. So when someone asks how much of the climate change is down to humans, the correct answer is all of it. It's actually, when you break it down, competition between two competing components. One is well-mixed greenhouse gases, about a 1.5 degree contribution, and the other is other human drivers, principally particulate matter aerosols, which has a negative effect, and the balance of those comes to that about 1.1. You'll note no solar or internal variability. We looked at in another way at it, which increases the confidence, whereby we translated those radiative forcings from the earlier diagram I showed you into temperature contributions. And there you can see that carbon dioxide is the major contributor, but there are significant contributions from methane, from nitrous oxide, from sulfur dioxide, the aerosols. So this is complementary. The fact that we get the same answer from fundamentally distinct techniques, complementary approaches, increases the confidence in our attribution. Temperature is one thing. There are many other components of the climate system that are changing in fundamental ways. Global average precipitation has likely increased since 1950 and faster since the 1980s, and that human contribution to that has been detected. It's a likely influence in IPCC parlance. And there are other aspects of the hydrological cycle that have also changed due to human influence. We can also go to the frozen component of the climate system, the cryosphere. And there again, we find both that it is changing and that human influence is a major contributor. The panel on the left here is a simple count of the number of glaciers that were advancing over the past 2,000 years, the Common Era. And you can see that many glaciers were advancing, particularly in the last 1,000 years, right up until very recently, when suddenly that drops off a cliff. That drop, that globally synchronous glacier loss, is a huge signal of human climate change. It is very, very unusual in the context of the historical record to see such globally synchronous retreat. Global mean sea level has increased, and that human influence is likely the main driver of these increases since at least 1971. Global mean sea level has never been static. Changes in the top left-hand panel here, between consecutive glacials and interglacials have been hundreds of meters. There are periods prior interglacials in which sea level has been higher. Sea level has risen very quickly in the past 2,500 years, or in the last 100 years relative to the last 3,000 years, sorry. The sea level takes a long time to equilibrate. This will be gone into in more detail in the later talk by Tamsin, so I won't steal the thunder there, but sea level is really important. But it's not just the sea level that's changing in the oceans. Ocean heat content is increasing rapidly. That ocean heat content is extremely likely due to human influence. Ocean heat content takes most of the energy that is going into the Earth system. We have also acidified the oceans, ocean acidification down to CO2. And there is also high confidence that oxygen levels have dropped, and there is medium confidence in a human contribution to that drop. And again, these changes are highly unusual on the long-term basis, based upon proxy evidence. A unique thing in this IPCC compared to all prior IPCC reports is that we looked at the biosphere in some detail. We looked at climate zones, global greening, global browning, other aspects, but perhaps one of the easiest to communicate aspects is the changing phenology. We have some very long time series that go back at annual resolution to 1400 or earlier for a very small number of sites. We have more as we come forwards in time. All of these show a kind of hockey stick or inverse hockey stick, if you like, that changes are occurring in multiple aspects. So cherry blossom peak bloom in Kyoto in Japan is becoming earlier. The grape harvest in Bern in France is being taken earlier in the year, and so on and so forth with these various indicators. All of them point to a fundamental shift in the biosphere, in the timing of key events in the life cycle of the biosphere. We can also take a much, much longer view on climate, and we can see how unusual we are, and we can look at how prior states might map onto states we might see in the future. So we really did look at how we can use the past to tell us something potentially about the future of climate. This is a rich graphic that I wouldn't expect you to take a huge amount from immediately, and looking at it, it does provide a guide to where we were in the past and where we might be in the future. So taking, for example, the mid-Pliocene warm period, which is the third column up from the third row up from the bottom, that's when CO2 was last around where we were today. Temperatures were 2.5 to 4 degrees warmer than today. The northern tree line was 4 to 10 degrees closer to the pole, and sea level was between 5 and 25 meters higher than today. That tells us where, after the Earth system reaches some kind of equilibrium, climate or key aspects of the climate was relative to today. And that's quite scary. So to sum up, it's unequivocal that human influence has warmed the atmosphere, ocean and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere and biosphere have occurred. The scale of those recent changes across the climate system as a whole and the present state of many aspects of the climate system are unprecedented over many centuries to many thousands of years. Those are the two key headline statements that relate to observed changes, their causes and their unusualness. It is a very strong message, a very strong alarm call that we are changing the climate system in really important ways. And with that, I will stop presenting and hand back to Tim.
Thank you very much, Peter. That was very informative. And questions will come at the end. Please put them in the chat. But for now, we're going to move swiftly on to our next speaker. So if Amanda could start to share her presentation while I give a brief introduction. So Amanda Maycock from the University of Leeds in the UK. She was a lead author for Chapter 4 on future projections of climate change. And that's what Amanda will now present. So over to you, Amanda.
Thanks very much, Tim, for the introduction. Can you see my slides now?
Yes.
Great, thank you very much. Well, good morning, good afternoon, good evening, everybody. It's a pleasure to have the opportunity today to talk to you at this important meeting, summarising the findings of the recent Working Group 1 AR6 report. So as Tim's introduced, I was a lead author on chapter 4 of the assessment, which was concerned with future global climate, scenario-based projections and near-term information. So I'm going to focus on that aspect in this presentation. And what I want to try and do is to first give you an overview of the things that I think are quite new in AR6. So obviously AR5 presented projections as well. So I want to tell you a bit about what's new, and in particular go into some details about the new methodologies we used to make projections for global temperature changes over this century. So I'll spend a bit of time on that. So just to kind of give you a few bullet points of things to look out for as you're reading the assessment and going through the projections across the assessment. So you'll notice that the AR6 as a whole has a new structure compared to AR5, and in particular, I'm going to be focusing on these what we call the global chapters 2 to 4. So you've just heard from Peter on chapter 2 about the observations of changes to the climate system. Chapter 3 handles the human influence, and then chapter 4 is on the projections. So what we've done is to build a good connection across those chapters in terms of the global climate indicators that they focus on. In AR5, there were 2 separate chapters that dealt with the near-term and the long-term projections. Here they are combined together in chapter 4, so that's new. And we focus on a range of things that we consider to be global climate indicators. So these are kind of obvious things like the global surface temperature, but also things like the land precipitation changes, the global monsoons, and also a lot more material and focus on large-scale modes of variability across chapters 2 to 4. We present scenarios we present 5 different illustrative scenarios for projections. So that's an expanded set of scenarios than you would have seen in AR5. In particular, we now have the shared socioeconomic pathway scenarios, SSPs, and we have included the SSP 119 scenario. So that's particularly pertinent in light of the Paris Agreement having been signed in the interim period since AR5, looking at very low emission scenarios. And we also include at the upper end 2 other 2 scenarios. So there's the very high emissions 585 scenario, but we also include a lot more information on this SSP 370 scenario. So a sort of intermediate upper end scenario. There's been some literature recently talking about whether SSP 585 should be considered unrealistic now. And current emissions commitments put us on track for somewhere between SSP 245 and SSP 370 in terms of the kind of current pledges and the nationally determined contributions. So you'll see 5 scenarios presented. We have a much more in-depth consideration of internal variability and its role in projections. There's been a lot of work since AR5 using, for example, large ensemble experiments from climate models, and we could assess all of that material in the chapter. We've also taken a new approach to combining multiple lines of evidence to project certain variables. I'll expand on that in a moment with a focus on the global temperature projections. We provide updated assessments of when we might expect to exceed the 1.5 degree threshold that's one of the targets set out within the Paris Agreement. We have new models, of course, so there's the CMIP6 models, but there's also the use of what we call emulator tools, and I'll talk more about that later as well. That's across the Working Group 1 assessment, and it provides a connection into the Working Group 3 assessment, who have historically made a lot of use of kind of simpler climate models. And finally, we provide the projections for 3 different time periods. So we have the next 20 years, which we call the near term, we have the mid-century, and then we have the end of century, the long term. So we focus on those as the 3 kind of critical time periods for providing the projections. Okay, so I'm going to start by talking about something that's not in the assessment in this form, but it is considered extensively in Chapter 7, and that's the assessment of climate sensitivity. So in AR5, the assessed likely range, that means the 66% probability range for the parameter we call the equilibrium climate sensitivity. So that's the temperature change that would occur at equilibrium from a doubling in CO2 compared to pre-industrial levels. That range was assessed to be between 1.5 and 4.5 degrees Celsius. So that was the ECS assessment. Now in AR6, that range has been updated extensively in Chapter 7, so I'll refer you there if you're interested. And the likely range in AR6 assessment is 2.5 to 4.5 degrees for the ECS. So that uncertainty range has narrowed. There's been a lot of new work since AR5 on assessing lines of evidence for ECS. So these ranges are kind of indicated on this diagram on the right-hand side here, and the grey box is the AR5 range, and this red box is the updated AR6 range. Now, also plotted on here are two sets of climate models. So there's the CMIP5 model shown in blue, and CMIP6 models shown in the orange points here. And what you'll see here, what you'll notice, and some of you may be aware of this already, is that there are a number of CMIP6 models that exhibit climate sensitivities that are either unlikely or very unlikely to be representative of the Earth, according to the IPCC assessed ranges. So there's a whole bunch of models here which have much higher climate sensitivities. In AR5, it so happened that the CMIP5 model climate sensitivities happened to sort of fall within the assessed likely range, and we didn't have so many high sensitivity models. There's been a lot written about this in the literature and in the press already, and I don't have time to expand on it all now, but this is just to make you aware that the CMIP6 models do have, some of them do have these higher sensitivities. So this obviously has implications in terms of using those models to make projections for the future. And in AR5, the assessed global temperature projections were based solely on the CMIP5 model data set. So the projections from those models were used to inform the assessed temperature projections. And the way that was done was that the 5 to 95% range of the CMIP5 models was interpreted as the likely or 66% probability range of the assessed temperatures. Essentially what they did was to add on a bit of uncertainty to the climate model projections to account for the sources of uncertainty that are not comprehensively included in that CMIP5 data set. So obviously they're just a finite set of climate models. They're not designed to span all known sources of uncertainty in a comprehensive way. But the information solely came from CMIP5. What we've done in AR6 is to use new methodologies to combine multiple lines of evidence to make those temperature change assessments, and also the ocean heat content projections and thermospheric sea level projections, so things that are also tied into the global temperature. And those lines of evidence are listed here. So they include the observational constraints on the warming rates. So we obviously have observational data on recent historical warming, and we can compare the modelled temperature changes over that period to what was observed. We have the information from the CMIP6 model dataset, and we also have the assessment of climate sensitivity that I've just gone through on the previous slide from chapter 7, and we can use that within a simple climate model to come up with temperature projections based on basically an energy balance model setup. So just to kind of show you what this looks like in a figure then. So here I'm showing you, this is a figure from chapter 4, and it basically shows temperature projections for the end of the century. So these are global temperature anomalies by the end of the century relative to the present day in the 5 illustrative scenarios that I've introduced. And what we show here are results from 3 different studies who have looked at these projections from CMIP6 models, and they're all shown here in the 3 different coloured bars. So obviously higher warming as we get towards the higher forcing scenarios. Now, what these studies do is basically try and constrain the spread of these models using information from recent historical warming. So by looking at the warming rates over the last 20 years, say, comparing those against the models and then applying an emergent constraint relationship to the model spread, what they've been able to do is to narrow the spread in these projections from the models. And what you'll notice in particular is that the upper end of the warming in these projections is reduced. So that's essentially telling us that some of the CMIP6 models have warmed more over the last 20 years than we've observed, and we can constrain and sort of downweight those models going forwards in the projections into the future and come up with a narrower uncertainty range by using that constraint. And that's what's been done here. So that's one of the lines of evidence that has been used. The other, and so what we do is take those 3 different approaches. They're related approaches, but they're from independent studies. They actually agree with each other quite well. So we can just average those 3 approaches together to come up with a constrained CMIP6 temperature projections. That's shown on the bottom left here in the grey bars. And then we also have the results from these simple climate model emulators, these energy balance type approach models, using the assessed ranges of climate sensitivity from the assessment. And those are shown in the green bars here. And actually, what we found was that the 2 approaches are in rather good agreement with each other, as you can see here. And so we then, to come up with the assessed temperature changes, we just average the two approaches together. They're actually in such close agreement that we were able to do that. So the bottom right here shows you the kind of culmination of those steps, which is our assessed global temperature changes over the 21st century in the 5 illustrative scenarios. And this, as I've said, these results are combined from these multiple lines of evidence rather than just taking the raw CMIP6 models as being representative of what we think the projections will be and just taking that as a single source. So that's very new in AR6. We're then able to go forward and to decompose in the scenarios the contributions from different radiative forcing agents to the temperature changes by the end of the century. So these are temperature anomalies, again, at the end of the century relative to the pre-industrial period or the early pre-industrial estimate. And you can see that in all of these cases, of course, we know today carbon dioxide is the largest contributor to current warming, as Peter's just told us, and going forwards into the future, that obviously continues in all of the scenarios. But there are also important contributions to warming from non-CO2 greenhouse gases as well, which you can see in these third bars in the rows here. So you can find this is a figure from the summary for policymakers, which makes that breakdown of the contributions to warming in those scenarios. And so based off this evidence, the SPM was able to conclude that to limit warming, strong, rapid and sustained reductions in CO2, methane and other greenhouse gases are necessary, and that would not only help to avoid further climate change, but it would also improve air quality. So there's kind of a dual benefits for trying to take those steps. We provide updated estimates of when we can expect to cross the 1.5 degrees warming threshold. So the first thing to say is that in the last decade, the planet was just under 1.1 degree warmer than the 1850 to 1900 period. So we've already, we're not far off 1.5 degrees of warming already, I guess is the first thing to say in the observations. So if we project forwards into the future, in the 5 illustrative scenarios, this is just a table pulled from the chapter where we provide the very likely, so the 5 to 95% range of estimates for when the 1.5 degrees threshold would be reached or exceeded. And what you can see in all of these ranges is that you know, this is happening in the not very far future. So you're talking about somewhere in the sort of mid 2030s as being when we would be very likely to exceed the 1.5 degrees in all the scenarios. Now, there was some discussion in the kind of after the release of the report about whether this was disagreed with the SR 1.5 report statement on reaching 1.5 degrees. You might remember in their summary for policymakers, it was said to be likely that global warming would reach 1.5 degrees between 2030 and 2052. So obviously the midpoint of that is around 2040. That was based on extrapolating the current rate of warming, which was about 0.2 degrees per decade. Actually, in chapter 2 of SR 1.5, they also provide scenario-based information for crossing times, and they're actually in very good agreement with AR6. So the point is that all these things are telling us that it's not a long way away. And indeed, the statement at the publication of the report was that, you know, unless there are immediate, rapid and large-scale reductions in greenhouse gases, limiting warming to 1.5 degrees will be beyond reach. The sort of final thing I wanted to highlight was just the use of warming levels in the projections chapter and across the assessment more widely. So these are just maps showing you the changes in precipitation at warming levels of 1.5 degrees, 2 degrees and 4 degrees relative to the pre-industrial period. And this has been a very valuable approach to look at things in terms of the impacts that can be expected at different warming levels, and it connects in nicely to the extremes chapter, which Sonia will talk about next in terms of looking at changes to extremes. I just want to finish by thanking my colleagues on chapter 4. Any of you who've been involved in these reports before will know it's an extraordinary effort for the community to kind of work on these reports. You know, this has taken several years and we've had a global pandemic in between. So I just want to say, you know, this is really a team effort, and we were very fortunate to be led by 2 fantastic scientists, Junie Lee and Jocko Morozka, as our CLAs on the chapter, who kept us all in check. And we also had 2 fantastic chapter scientists who did a huge amount of the legwork on analysis and figures, etc. So just to summarize then, we've used a new approach for producing projections of global temperature and some other variables in AR6 compared to previous assessments. So that's something to look out for. We've combined multiple lines of evidence. The headline statement is that 1.5 degrees, limiting warming to 1.5 degrees Celsius is still within reach, but to do so will require immediate, rapid and large-scale reductions in emissions. We've focused in the chapter on a range of global climate indicators. There's a much more extensive assessment of modes of variability if you're interested in global modes of variability. We've used warming levels much more extensively in AR6. And also there's this nice handshake through to the Working Group 3 assessment through the use of these emulators for projections. So in Working Group 3, they look at many, many more scenarios. We've used 5 illustrative scenarios. In Working Group 3, they're looking at hundreds of scenarios. And so they use these emulators much more extensively. And we've tried to embed that more thoroughly within Working Group 1. So thank you very much for your attention. I look forward to answering questions later.
Thank you, Amanda. I think you explained some really quite complex concepts very lucidly, so thank you for that. So now we come to our last talk of this first block. So please get your questions ready for the Q&A session and start posting them in the chat. But first of all, we have Sonia Senavaratni from ETH Zurich in Switzerland. And Sonia was coordinating lead author of Chapter 11 on extreme weather and climate events. And that's the topic of her presentation today. So if you could please share your screen, Sonia, and then start when you're ready.
I'm not sure if you can see my slides. Yeah.
Just coming up now, I think.
Okay, perfect. Yeah. So
they haven't quite appeared actually. Oh, here we go. Yes, they're on here now. So over to you.
Okay, thank you very much. So yeah, I thank the organizers for the invitation. It's a great pleasure to make this presentation. I will present the main conclusions we have on changes in extremes and surprise in the report, and this is mostly based on material from the Chapter 11. So to start with the changes that have been observed, we can say that the evidence of observed change in extremes has strengthened. That's really one area where we have much stronger evidence compared to the AR5. And we can also assess that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. So that's a really important message, that no region is spared, really every region is affected. Some recent hot extreme events would have been extremely unlikely to occur without human influence on the climate system. So we're starting to see events that basically we could not have seen without human-induced climate change. And the extremes that have been assessed are listed below. So we looked at temperature extremes on land, but also in the ocean, heavy precipitation, floods, droughts, storms, and also compound events, including, for instance, fires. So about observed changes in hot extremes, this is one aspect where we have very clear evidence, really, in almost all regions of the world. So the assessment is that it is virtually certain that hot extremes have become more frequent and more intense across most land regions. And there is high confidence that human-induced climate change is the main driver for these changes. So you see this map here, which is showing in which regions of the world we are seeing an increase in hot extremes. You see that this signal is very clear, really, in the overwhelming majority of regions.
Sonia, sorry to interrupt. For some of us, at least, your slides aren't advancing. I think most people perhaps can still see only your title slide. I don't know if you can.
Oh, sorry.
I think maybe we can advance them manually. We have a control on our team.
Sorry. Okay. So I was sharing my slides here. So should I try again? No.
Yeah, could you try moving forward one slide?
Yes. Do you see them now or not? Okay, sorry, yeah.
I think that's now working for me. So hopefully that's working for everyone else as well, and back to where you were.
Okay, very sorry about that. Yeah, so I was showing before the changes in hot extremes. In terms of heavy precipitation events, the frequency and intensity of heavy precipitation events have increased since the 1950s over most land area for which observational data are sufficient for trend analysis. You see here the map where we have the assessed changes in heavy precipitation events. And you see that in the majority of regions where we have data, we see a clear increase in heavy precipitation. And so human influence, in particular greenhouse gas emission, is likely the main driver for these observed changes in heavy precipitation. Regarding changes in droughts, human-induced climate change has contributed to increases in agricultural and ecological droughts in some regions due to increased evapotranspiration. You see that several regions here highlighted in yellow show an increase in droughts from observation that's substantially more than what was assessed at the time of AR5. Regarding tropical cyclone, it is likely that the global proportion of a major tropical cyclone, so the most intense one, has increased over the last 4 decades, and this change cannot be explained by internal variability alone. Human influence has also likely increased the chance of compound extreme events since 1950s, and increase in the frequency of concurrent heat waves and droughts on the global scale are seen, and this also includes increase in fire weather in some regions in all inhabited continents, and increase in compound flooding in some locations. So this is an important new aspect, changes in compound extreme events. So we are looking at the co-occurrence of different type of extreme at the same time, either at the same location or different locations. So I'll say a few words about projected changes in extremes as function of global warming. That's also an important new aspect on which we have a lot of assessment. So many changes in the frequency and intensity of climate extremes become larger with increasing global warming. That's the case for hot extremes, for marine heat waves, for heavy precipitation, for agriculture and ecological droughts in some regions, and also for the proportion of intense tropical cyclones. So we've seen in figure the presentation of Amanda that we have these increasing changes with global warming. That's the case for mean changes, but also for extremes that you see here, the projected changes in annual maximum temperature with clear increasing changes with higher global warming levels. So in the summary for policymakers, there is quite extensive material on changes in extremes. The projected changes in extremes are larger in frequency and intensity with additional increment of global warming. That's a really important message from the summary for policymaker. So from the literature, it is clear that you see substantial difference for half a degree of global warming, but also you can infer from the direct relationship of changes in extremes with global warming that really any increment of global warming will matter for change in extremes. For instance, for the frequency of hot extremes, you see here the change in the frequency of an event that would have happened about once every 10 years without human-induced climate change. Under present-day climate, at around 1 degree of global warming, or rather 1.1, this type of event is occurring about 3 times every 10 years. At 1.5 degrees, this type of event would rather happen 4 times every 10 years. And you see this increase with almost every year being affected by these hot extremes at 4 degrees. Also, the intensity of extremes is increasing, and as we have seen also in the presentation of Peter, the temperature on land are increasing more, so this is also affecting hot extremes. You see that the increase in intensity of hot extremes here is substantially larger than the change in mean global warming. So at 1 degree, we have about 1.2 degree warming in hot extremes. At 1.5 degree, we would be at about 1.9 degree. Finally, in terms of the rarity of the events, if you're looking at the change in frequency in very rare events, you see actually that in proportions are increasing more. So for instance, if you're looking at statistics for changes in frequency in the 1 in 50-year event, which is shown here on the right, this event is happening about 5 times more frequently now compared to climate without human-induced climate change. So it's a larger number than in the case of the event that was happening only once every 10 years. In terms of projected changes in heavy precipitation and droughts, I'm showing here the projected changes for heavy precipitation. We have similar conclusions, so basically both an increase in frequency and intensity of those extremes. You see that for heavy precipitation, so you have a gradual increase with increasing global warming. We have also very clear conclusions regarding the change in intensity of heavy precipitation with an increase of approximately 7% with every degree of global warming. Regarding changes in agriculture and ecological droughts, so that these are droughts affecting the water availability in the soil, affecting agriculture and ecosystems. We also have clear signals here assessed for drying regions. So these are the regions at which we have an assessed drying at 2 degrees of global warming. This is shown on the map on the right. So average over those regions at present, more or less 1 degree of global warming. These events are more or less happening 1.7 times more frequently than without human-induced climate change. At 1.5 degrees, it would happen twice as frequently, and you see that the frequency further increase with increasing global warming. And again, intensity is increasing with global warming. So the main summary of all this is, with increasing global warming, the changes in extremes are getting worse and more stronger. So I will say a few words also on compound events and surprises. So with further global warming, every region is projected to increasingly experience multiple changes in climate impact drivers, including extremes. And many regions are projected to experience an increase in the probability of compound events with a higher global warming. So we have on the one hand an increase in the concurrent heat waves and droughts, also further increase in fires and compound flooding. And we have an increase in the probability of concurrent extremes at multiple locations. One example is, for instance, having extremes at the same time in different crop producing areas, which would be more likely at a 2 degree compared to 1.5 degree. Of course, this would have, for instance, implication for food security. There will be also an increasing occurrence of some extreme events unprecedented in the observational record with additional global warming, even at 1.5 degree of global warming. And I think this is a really important point. I've mentioned before already in the observation, we are starting to see events which are unprecedented, where we can say with almost certainty, basically these events would not have occurred. And so those events, of course, are also associated with more surprise because they are quite different from what we have experienced in the past. And such events are going to become more frequent already also at 1.5 degree. And I think another really important point is sometimes we are surprised by some of the changes that are happening. In reality, if you're looking at the statistics, you find that some of those events that were considered quite extreme actually didn't have a particularly low probability in the present climate, but they can be perceived as a surprise because we have a very high pace of global warming. So the change in the climate system is happening very quickly. So to come to the conclusions, research on extremes reveal much clearer signals of the effects of human-induced climate change on change in climate extremes compared to AR5. Observed increase in extremes are already identified in all regions of the world, so really all regions are affected. And changes in frequency and intensity of extreme events increase with every increment of global warming. And to come, I think, to the last point that is really important, is a world limiting global warming to around 1.5 degree would avoid numerous additional changes in extremes compared to 2 degree. But it would also be affected by additional changes in unprecedented extreme events compared to now. So a world at 1.5 degree to some extent would not be a safe world. It would be still worse than what we're experiencing at the moment. And yeah, thank you for your attention. I just want to share also this picture of the authors of chapter 11. And as Amanda has mentioned, this was work in very special circumstances, but yeah, I'm very thankful to all the contributors to this chapter. Thank you very much.
Thank you, Sonia. And thank you for an informative talk and for keeping to time. And now is the time for people to put questions in chat. I think one thing we missed from physical meetings is the direct feedback from the audience, but I'm sure our participants are all joining me in thanking you for 3 wonderfully informative presentations. I'm going to select some questions from the chat, but while I do that, if the 3 of you could put your videos and mics back on, or you already have done, you preempted me there. Thank you very much. Okay, so we've got some questions coming through in the chat. I'll start off with Peter Irvin's question, which I think is for Sonia. He says the response of extremes at the global scale looks pretty linear. Could you comment on the linearity of the changes in climate impact drivers?
Mm-hmm. Yeah, so if you're looking at the intensity of climate extremes, this is generally changing more or less linearly as a function of global warming. An important point is if you're looking at the changes as in terms of frequencies, these are non-linear. So basically for thresholds which are relatively rare, actually at the start the increase are rather exponential. So that's also another important point.
Thank you for that. We next have a question for Amanda. This question comes from Vicky Thompson. How cautious should we be when looking at future projections in CMIP6 models that have higher climate sensitivity? Are they still useful for looking out to the end of the century?
Thanks, Vicky. Yeah, great question. So one thing I didn't mention, but is also new in chapter 4 this time around, is that we include what we call low likelihood, high impact scenarios. And so what we would say is that some of these CMIP6 models that do have, climate sensitivities that are quite far outside of the assessed likely or very likely range of ECS from chapter 7, unlikely but not impossible scenarios that we could follow. And so looking at them in those terms can be valuable, particularly for people who want to, different sectors who may have different tolerances to risk, may want to examine some of those scenarios that we call these low likelihood, high impact outcomes, just to stress test systems or whatever. But and so, it had been criticised previously from AR5 that maybe sometimes we just focus too much on the kind of central estimates or the kind of likely ranges, and we don't say enough about the kind of upper tails of the distributions. And we've tried to do that more comprehensively this time. Thanks.
Thanks, Amanda. We've got a question now for Peter from Catherine Brown, which was on my screen a minute ago, and now it's been replaced by something else.
I can see it there. I can see it out. So
Everybody else, please, Peter.
So the question was, have we had pushback on the message that humans are 100% responsible? So yes, one of the principal changes is that all prior assessments, starting with the second assessment report, which said balance of evidence, have become progressively more confident in terms of attribution, and now attribution is made unequivocally. AR5 did frame the human contribution in a way that got misinterpreted by those interested in spreading disinformation, and we tried to frame AR6 in such a way that that would be incredibly hard to do. And as far as I'm aware, we have had no substantial feedback to the messaging that human contribution is 100% of the observed warming, and that's scientifically robust and benefits from multiple ways of looking at the problem, all coming to that conclusion. So it's very robust. But yes, undoubtedly there will be criticism of it. I just think they haven't worked an angle out yet to do so.
Thanks, Peter. And I think that attribution statement is very hard to word. I think not just the previous assessment report, but the one or two before that also found difficulty in getting wording that was unambiguous. So thanks for that. We have another question now for Sonia from an unknown user. The distinction between different types of drought seems very important now. The event attribution studies often focus on meteorological droughts. Do we now have good enough data to start to do event attribution for agricultural or soil moisture drought?
Yeah, that's a good point. So this was the main focus of the report, that we are distinguishing between different types of droughts. On the one hand, meteorological drought, which is only related to precipitation, and also agricultural and ecological drought, which is rather related to soil moisture. So, and then we also have hydrological droughts, which is related to runoff. So in terms of attribution, it's true that many studies focus on precipitation. I would say, in principle, it should be possible. So I know at least for some studies which are not like real-time attribution studies, it's possible, and it has been done in the past. We need good products for that. I mean, you could also use products from the analysis to some extent. So yes, I think we can move towards this. And the importance of that, on the one hand, it's more relevant for impacts. So availability of moisture in the soil affects vegetation directly, so it's really what we should care about. On the other hand, the signals are substantially different, because in the context of climate change, change in evapotranspiration is an important driver for the drying, and that's very clear in the data.
Thank you, Sonia. Back to Amanda now. I have a question again from Catherine Brown. Could you say something about at what point we'll know if we've exceeded the 1.5 degrees goal or not?
Yeah, absolutely. Thanks, Catherine, for the question. So, yeah, you make a very good point. And indeed, the projections for the sort of timings that we give are based on the kind of midpoint of a 20-year window where the 20-year average exceeds 1.5 degrees. So we're not just looking at, intentionally not just looking at a single year overshooting. And for exactly the reason that you highlight, that we know there's internal variability from year to year, and we may temporarily exceed 1.5 degrees and then go back down again. You know, and so we're talking about a sustained exceedance over a 20-year window. We were very mindful of what will happen and the kind of reporting that will happen if a year does go over 1.5 degrees, you know, coming up, and we'll have to kind of carefully determine that. But it's clear from the Paris Agreement that when they talk about 1.5 degrees Celsius as a target, they're talking about a sustained level of temperature change, not just a single year. Thanks.
Thanks, Amanda. And I'm actually going to come back to you, Amanda, although others can chip in if you want. I'm going to try and combine two questions together as well. So Neil Harris and Roy Thompson have asked about the CMIP6 climate sensitivity conundrum, as Roy puts it. Roy asks, for example, does this imply that we still need a significant or step change in the climate models, improvements in them presumably, to address the fact that you're essentially downweighting some as potentially unrealistic? And Neil asked about emulators and how independent they are from the CMIP6 models. So perhaps emulators as the way forward rather than better physical models. What do you think?
Yeah, thanks, Roy and Neil. So yeah, very interesting discussion, and I'm sure, you know, it sounds like you're aware of some of the you know, pieces that have appeared from certain scientists advocating for kind of new approaches to how we do climate model development internationally. I think there are, you know, pros and cons of different approaches, of course. The limitation of sort of combining forces and having, you know, kind of one super model that many groups contribute to would be that we wouldn't be able to put an error bar very easily onto that model in terms of understanding its structural uncertainty. We know from the multi-model ensembles like CMIP that, you know, there is substantial structural uncertainty across models in certain aspects, and it's important that we can explore that in some way. Equally, I think, you know, what we've seen in CMIP6 is, and it's still ongoing, you know, the scientific evidence and understanding of the CMIP6 models is, of course, still ongoing. And I think, you know, what we've learned so far is that in some cases, you know, the models verify against observations in certain aspects better than the predecessor models did. So, for example, with respect to their representation of mixed phase clouds in certain regions. But obviously, when you then look at, you know, that's a kind of verification in the modern climate. If you then project that model forwards into the future, it produces a very high warming. So there's, you know, the climate sensitivity is generally considered as a sort of emergent property that comes out of many different processes and feedbacks in the model. And so it might be that certain processes are now improved, but others perhaps still have work to be done on, and so the resulting climate sensitivity has kind of gone up. So it's a complex picture, but I agree. I think it's interesting debates now we're starting to have about the way forwards, and as we start to looking at cloud resolving, you know, storm resolving kind of climate models and things like this in exascale computing, we are going to have to be thinking as a community quite seriously about how we sort of approach what we're doing. Just to answer Neil's question quickly before we move on about emulators. So the assessment of climate sensitivity in Chapter 7 was based very heavily on some work led by Steve Sherwood, but a huge community effort that's taken many years. And what they did there was to try and use lines of evidence that are not directly tied to the climate model ensembles. So they've looked at paleoclimate information as a constraint. They've looked at historical temperature change as a constraint, and they've looked at process-based studies around kind of cloud feedbacks, for example, and used those and combine those lines of evidence to estimate, you know, the assessed range for climate sensitivity that isn't directly tied to the multi-model ensembles. So I think that's nice now that we have that kind of separation between, you know, the climate sensitivities that CMIP models produce, and we can critically assess those now in light of the climate, the ECS assessment that was made through other routes of evidence. So yeah, thank you.
Okay, thank you. We're getting some good questions, good answers here. Still time for some more as well. If you've got any questions, especially for Peter, then please put them in the chat so he's not left out. Got a question here from John Mathven. Crossing times for 1.5 degrees Celsius seem to be approximately independent of the SSP scenarios. Perhaps this could lead to some complacency. Why is it going to happen anyway? Who would like to comment on that? Is that back to you again, Amanda?
I guess I could take this one quickly and then hand over to someone else. So yeah, John, you're right. I mean, that's for two reasons, really. One is that we're already quite close to 1.5 degrees already today. And the other is that the scenarios don't diverge very much in their forcings over that kind of next 20-year period. So you're right that they do have broadly similar crossing times. In the chapter, we do provide crossing times for 2 degrees Celsius as well. I didn't show those because of lack of time, but you can find those in the chapter as well. I think the important thing to note, and it was very carefully worded in the SPM, is that the 1.5 degrees will be reached or exceeded in all of the scenarios. The important thing is that although the SSP 119 scenario shows a small overshoot, or it's likely there'll be a small overshoot around mid-century, if you look at the end of the century, the temperature is projected to come back down and stabilize below 1.5 degrees. So that would be the route to achieving that 1.5 degree target, but it's only really possible in that scenario. And if you look at the longer term changes at the end of century and all the other scenarios, then there's a high degree of likelihood that they would be over the 1.5 degree threshold. So that's the important thing that we were trying to stress, I think, in the chapter. Thanks.
Okay, thank you. We have a question for Sonia, which I don't quite understand. So if you don't understand it either, Sonia, then we can ask for a clarification. But the question is, are the intensities in figure SPM 6 for the most extreme events, or are they for the average of those events that pass the natural 10-year return value?
Mm-hmm. Yeah, no, I think I understand the question. So the answer is, well, I mean, it's basically, I've shown two figures. One was for the 10-year event, the other one was a 50-year event. So this, of course, represent two different parts of the distribution of extremes, but we are not looking then extra to the most extreme part of those extreme events. So basically, the statistics are provided for the mean, if you want, of those 10-year events, or the mean of the 50-year events.
Thanks, Sonia. I think we have until 12:05 till the talk start again. Someone correct me if I'm wrong. So I will take some more questions. There's a question here for Amanda again from Gabby Hegel. And actually, this is a question I'd written down in case there was a lack of questions and I had to ask my own. So I'm glad to see that coming up, which is about the observational constraints between emulators, etc. And you said, Amanda, that these apply to some of the variables and aspects you're considering. But what variables are observationally constrained? And my question was what do we do about the ones that aren't?
Yeah, thanks, Gabby, for the question, and Tim. Yeah, really important comments. So as you know, within IPCC, we don't do new science, we assess the published science. And so we would have liked to have been able to to kind of take similar approaches to other variables, but there just isn't the scientific basis for doing that at the moment. So what this was applied to in the chapter is the global temperature projections. They're obviously very prominent. Also the thermospheric sea level change and the ocean heat content projections. So those are the kind of three variables where we were able to combine the information in that way but for other variables, so all of the assessments of modes of variability, changes to sea ice, and all the many other things that are assessed in the chapter, those were based on the CMIP6 model ensemble. So yeah, I personally think that, there's an opportunity there to think about developing these sorts of methodologies in other aspects of understanding projections in the climate system. It was just that we used what was available at the time.
Thanks, Amanda. I think we've got time for one more question, probably. No, probably two more, actually, looking at time. So first of all, for Peter, how far back do you think it's feasible to extend the thermometer-based estimates of global average temperature? And that's come from Steve Smith.
Okay, thank you. So one of the first things to be clear is we have a much broader range of estimates going back to 1850 in AR6 than we had in AR5, and that's a major advance. I think we can possibly push it back to 1800 or 1750. That depends upon how strict you are or otherwise with the term global in that. And there are interesting projects, which Tim is involved in, one of them, but there are several that are pushing back to try and see whether we can go to 1800 or 1750. We need to work on this harder, but I do think we can possibly push it back to closer to the true pre-industrial.
Thanks, Peter. Well, I think we can get our money's worth by squeezing in one more question for any of you, provided Yuri can get his slides ready while we're talking. so we can transfer quickly. So this comes from a guest. Some climate activists attract attention by focusing on the upper bounds, such as 4 degrees Celsius and large-scale civilization consequences. But this can play into the hands of deniers. So how do you communicate this nuance while stressing the severity of the issue?
I can take maybe this answer, and I would say you don't need to show the changes at 4 degrees to see sorry, I cannot pronounce this, but basically impacts on civilization. So anyway, and so I think basically what we are showing in our assessment is even differences between 1.5 degree and 2 degree are substantial. And I would say that's the main message for me. And it was also clear from the 1.5 report. Basically, avoiding 2 degree really avoids numerous changes. It avoids irreversible impacts. I would be very worried about 2 degree of global warming. I don't think we need to look at 4 degree to be worried about basically higher warming. Thanks,
Sonia, and thanks for keeping that brief as well. We're now going to move swiftly on to the second block of talks for this morning's session. So please start showing your slides, Yuri. And the second block of focusing on this IPCC's assessment of the risks and uncertainties associated with climate change. So first up, we have Yuri Rogel from Imperial College's Grantham Institute here in the UK, but originally from Slovenia. So Yuri was a lead author of Chapter 5 on the global carbon cycle and feedbacks. So this makes him the perfect speaker for this talk on emissions, the carbon cycle and the Paris goals. So over to you, Yuri.
Thank you. And I hope you can already see my slides, and I hope they will be advancing well. Indeed, I'm at Imperial College, and my grandparents come from Slovenia, but originally I'm from Belgium, just to be sure. That's the accent you can hear. I will be talking about the carbon cycle, emissions, and implications for policy, and starting at the very start of that journey. We have to look at the different scenarios and the different pathways that were considered in the IPCC report. Here you can see a figure about the 5 illustrative scenarios that are used in the AR6. They were already mentioned before, and they really represent different policy choices, and many of which are taken over the next decade. They range from scenarios, the very high and the high scenario, that involve rolling back some of today's policies and really not progressing with climate action as we are doing. A scenario that could be kind of in line with where we are today in terms of climate policy, and then 2 scenarios that attempt to achieve or limit warming below 1.5 and 2 degrees. Now, I want to look at the implications for the carbon cycle implications of these scenarios through 2 other figures of the summary for policymakers. The first figure basically shows, and the key message of the first figure is that the proportion of CO2 emissions taken up by land and ocean carbon sinks is smaller in scenarios with higher cumulative emissions of CO2. And what this figure basically shows is for these 5 scenarios that I showed in the previous slide, it shows the total cumulative amount of CO2 emissions in the gray bars. And then in the colored parts of those bars, you can see that that is the proportion, or it's the amount of CO2 emissions that is taken up by land and ocean. And what you can see here is that the higher the cumulative emissions, the higher the amount of CO2 taken up by land and ocean. And often in the scientific literature, this is referred to as the carbon sinks strengthening over time in scenarios with higher cumulative CO2 emissions. But if you then look at the donuts at the bottom, you can see a very different story. And you can see the donuts show the proportion of CO2 that is taken up by the land and the ocean sink compared to what remains in the atmosphere. And you can see that for higher emissions scenarios, like the very high emission scenario, the proportion of CO2 that is taken or that remains in the atmosphere is actually much higher. So this is a very important insight and a very important message that is highlighted in the SPM of the AR6. A second figure that I want to look at then to understand the implications of emissions for the carbon cycle and for policy is figure SPM5. And the main headline takeaway message of this figure is that every ton of CO2 emissions adds to global warming. And this is an update of an iconic figure from IPCC AR5. And what it basically shows us, here on the horizontal axis, you have cumulative CO2 emissions, and on the vertical axis, you have global warming. It shows the near linear relationship between these two quantities. And interestingly, it shows it both for the past. Here you can see historical warming versus historical emissions of CO2, and for projections. Again, here in the future, you can see for the 5 scenarios that we that I showed earlier, how all 5 of these scenarios, although they are very different in their shape and also in the contributions of non-CO2 greenhouse gases, they pretty much also lie on a straight line. That really means that to first order, these scenarios are very similar, and cumulative CO2 emissions determine future global warming. The SPM highlights this explicitly, and also importantly highlight that this relationship implies that reaching net zero anthropogenic CO2 emissions is a requirement to stabilize human-induced global warming, and also that this thus underpins the concept of a carbon budget for limiting warming to specific levels. And that is the next point that I would like to look in, the next point of the AR6 that I would like to look into. In the AR5, it was actually the first time that the IPCC provided or assessed the concept of a carbon budget and provided estimates. These were then updated in the special report of 1.5, and already there, 5 components were identified that need to be assessed and that can then be combined to understand the remaining carbon budget. The first of those 5 components is the historical warming. Of course, the closer we are to 1.5 or 2 degrees, the smaller the carbon budget. And here we use human-induced warming until the recent past. The next component that is of importance to understand the remaining carbon budget, and that has also been reassessed, is the transient climate response to cumulative emissions, or the TCRE, which is basically the inclination of this line between, or this relationship between cumulative emissions and global warming. And here, through a better integration of evidence across different chapters, including the climate sensitivity, we were able to narrow this range of the TCRE compared to the 1.5 report and the AR5. And now our best estimate is that that emissions of 1,000 gigatons of CO2 would result in approximately 0.45 degrees Celsius. Third aspect that was reassessed was the question whether warming will halt as soon as global warming, as soon as CO2 emissions are reduced to 0, or whether there is further warming. And here, actually, new evidence available since the 1.5 report shows us that our best estimate is that there is no further warming, but there is an important uncertainty range of about 15% of the total warming. Overall, it was assessed that it is relatively small compared to natural variability. You already heard from Amanda the important use of climate change emulators within the AR6, and that is also something that we have used to estimate the remaining carbon budget. As part of the estimates of the remaining carbon budget, we need to estimate how much warming non-CO2 emissions would produce at the time that global CO2 emissions reach net zero. And for that, we use these emulators, and which we apply to emission scenarios from the 1.5 degree special report. And there was a question earlier as well about how well these emulators perform. And here on the right, you can see a few examples of the extensive work within the IPCC that was led by Piers Forster and Malte Meinshausen on vetting and comparing these emulators to our best available evidence. For example, the top left, you can see how those emulators compare to historical warming and to observations. On the top right, you can see how they perform for the emulation of idealized CO2 scenarios, and then at the bottom, how they compare to projections that take into account the integrated knowledge of radiative forcing, climate sensitivity, and other observational constraints. And this is really an important advancement compared to earlier assessment reports. The last aspect, the last component that needs to be reassessed was the impact of Earth system feedbacks that would otherwise not be captured. Here we had a new assessment of the impact of permafrost, of wetlands, but also other atmospheric chemistry feedbacks, and which then ultimately will also integrated in the assessment of the carbon budget. Altogether, these 5 components can be combined in order to estimate the remaining carbon budget. And you can see here that you can see here on the right hand how they are combining, and then here at the bottom on the horizontal axis, one can then read of the remaining carbon budgets. What are these estimates then? What are these updated estimates? Here you see the overview table that was included in the summary for policymakers, and that provides key policy relevant information. It starts actually at the top, where both the human-induced global warming until the 2019 period is given, as well as the historical cumulative CO2 emissions that are largely responsible for that historical warming. That is really the starting point also then to look at the remaining carbon budgets that start from today and that provide our estimate of emissions in the future. Now, there are 3 normative choices that need to be made before a budget number can be given, and these normative choices are actually represented here in the many variations in this table. The first normative choice is the choice of the temperature limit. Of course, the carbon budget will differ depending on whether we want to limit warming to 1.5, 1.7, or 2 degrees. So these are represented here in the rows in this column. A second normative choice is the likelihood of effectively limiting global warming to a temperature limit if we stay within a certain carbon budget. Here we show 5 different probability levels, including the median, the 33 and the 67 percentile, and then we included 2 additional probability levels to also bracket the central 66% range of carbon budget estimates to give a good indications of the uncertainty. And the final normative choice is questions about how deeply we expect non-CO2 emissions, which of course also add to warming, can increase or decrease until the time that net zero is reached. This brings me then to the end with the takeaway measures, just that the proportion of CO2 emissions taken up by sinks is smaller in scenarios with higher cumulative CO2 emissions. Remaining carbon budgets in line with holding warming and well below 2 degrees holding warming well below 2 and 1.5 are very small, particularly compared to today's annual emissions of around 40 gigatons CO2 per year. And the next decade will effectively determine if we will keep warming to the goal set out in the Paris Agreement. And with that, I want to end with thanking also and acknowledging the contribution of the entire author team of Chapter 5. As the others have already highlighted, it is always a very collaborative and hugely international endeavor. So I just want to highlight their contributions. Thank you.
Thanks, Yuri. Another excellent talk. We're going to move swiftly on. Next, we have Richard Jones from the UK Met Office. So Richard was coordinating lead author of the Atlas chapter and involved also in the new online interactive Atlas for AR6. So Richard is going to tell us about the Atlas and also about regional climate change. So if you're ready, then away you go, Richard.
Okay, thank you very much, Tim. Just checking that you can hear me and see my screen.
Yes.
Okay, that's great. Thanks. So, thank you very much for the invite to speak to you today. So, I'm Richard Jones from the Met Office Hadley Centre and also Oxford University, and I was one of the coordinating lead authors on the Atlas, the Working Group 1 Atlas, which is a chapter in the report, but also has this additional component, the interactive Atlas. And I'm going to be saying, trying to summarise some of the results on regional climate change information that's in the report, mainly focusing on in what we have in the technical summary and some of the policy matters. So I will start by providing a brief overview of a new set of reference regions that we are using in the report. I will say something about a new concept which has been introduced into the Working Group 1 report, that these climatic impact drivers, which was referred to in one of the questions that was posed earlier. And I will then talk about the assessment process that we went through in terms of generating the information on regional change, and then show the main set of results, which are about the multiple and diverse sets of changes in climatic impact drivers that we are expecting to see across all regions, and close with a very brief run through of some of the functionality of the interactive Atlas. So the new set of reference regions that we're using in the Working Group 1 report comprise 46 land regions and 15 ocean regions. These were designed to improve the regional climate consistency within the regions, and to generate a better representation of regional climate features across the globe, and better, more representative of the output from the new high resolution models. They are a refinement of earlier reference regions, which was undertaken by a broad consultation, and the results of that were published in a peer-reviewed publication. As I said, we have an important new concept in the AR6 Working Group 1 report, which is climatic impact drivers, and these are physical climate conditions such as the average climate or particular events or extremes that are specifically things which affect an element of societal ecosystems, human or ecological systems. These are assessed across a range of chapters in the report. The main focus of this was in chapter 12, but it's drawing on information from chapter 8 on the water cycle, 9 on oceans, cryosphere and sea level, 11 that you've heard about already from Sonia, and also the Atlas, which assess mean climate changes. And the important point about these climatic impact drivers is that they were specifically selected and also through a significant consultation process, handshake process with Working Group 2 as relevant to impacts and risks. And what we have assessed in the report is a range of 30 of these CIDs over land and coastal regions and 6 in open ocean regions. And at the bottom, I'm just indicating that some of these climatic impact drivers are actually extreme events. So a few of these are the examples that Sonia was presenting earlier. Now, just a very brief overview of the assessment process that we went through, and this is detailed in chapter 10, and this is I think an important part of the report. So very explicitly, like you've heard earlier in terms of the assessment of climate sensitivity, we were integrating multiple lines of evidence to generate the findings on regional climate change. So we took information from observations, from attribution, and from projections, from understanding of the processes, and then we were basically we were considering all of those lines of evidence to generate a finding of our confidence in either an observed change or a future change from the models. And importantly, in addition to making it very clear how we went about this process, we also have documented all of this, so how all of the individual findings in terms of regional change for this range of climatic impact drivers, where they were coming from in terms of the underlying literature and the evidence that was used, that was drawn from that. So all of this backs up this very clear statement that human activities are causing climate change and making, in this particular case, extreme events, but also these wider set of climatic impact drivers more frequent and more severe, and this will continue into the future. So, so this is where we started to summarise the results. So this is a table for the technical summary, and I'm not expecting you to read all the detail here, but what this contains is, in the vertical, you have all of the reference regions that we were using in the report, and then in the horizontal, you have all of the climatic impact drivers, and the cells that are coloured in are where we have either medium or high confidence in changes, either increases in purple or decreases in brown. The white is where we don't have clear evidence, and the grey is where the climatic impact drivers are not actually relevant. So, for example, over much of Africa, permafrost is not a relevant CID. We then further sort of synthesized and simplified these findings into a figure in the summary for policymakers, figure SPM9. And what you're seeing here is looking for each of the climatic impact drivers, how many regions are they changing, either increases in purple or decreases in brown. And the shading that you see behind each of the bars is the number of the CIDs that are relevant. Sorry, is number of regions in which that particular CID is relevant. So what this shows is that for certain sets of CIDs, such as the heat and cold and the snow and ice and the coastal, we are expecting that these will change in the future in almost all regions. And then for some of the others, the wet and dry and the wind CIDs, you will in some cases have mixes of increases and decreases, but not all regions are necessarily going to be affected. But some of the key messages out of this is that there are at least 10 CIDs which will change in almost all regions, and for half of the regions you will see changes in at least 15 CIDs. So this makes it very clear that all regions will experience a significant and wide range of changes in these impact drivers. Now, just finally turning to the interactive atlas. So you can think of each of these bars here as representing a geographical set of changes, and the point of the interactive atlas is it allows us to explore in more detail some of these summary figures and some of the underlying information in the report. So on that, I'm just going to show a couple of views of the interactive atlas regional synthesis component. So this is the component which allows you to explore information either in the technical summary or the SPM. And this one here is showing for a particular CID, and this is fire weather. So that's essentially unpicking the bar in the previous chart on fire weather, where those changes are seen across the globe. So the dark purple is where we have high confidence that will change in the future, that will increase in the future, and the light purple is where we have medium confidence that will increase in the future. The white areas are where we don't have sufficient evidence, or we are not expecting change, and the grey areas are where that CID is not broadly relevant, in this case obviously Antarctica. The other view that I'm going to show we have in the regional synthesis is the ability to be able to pick a single CID from each of these groups of CIDs and see how that combination of CIDs will change across the regions. And here we are using this quasi-geographical representation of the regions, where each region is represented by a hexagon, and the information that you have in there is where you have the coloured triangles that shows whether it's increasing or decreasing and the level of confidence. The arrows are showing where we have observed evidence, or if it's coloured arrows, we have evidence of attribution of change. The final aspect of the interactive atlas that I would like to present is the regional information component. So as I said, there are two main components of the interactive atlas: the regional synthesis linked to the TS and the SPM, and the regional information which is linked to the main report itself. And also we draw a lot of information and figures in our chapter, in chapter 12, from the interactive atlas. So what this does is it has a very wide range of data sets which it has ingested for observations, both global observational data sets and regional, and then it has information from the CMIP5 and the CMIP6 and the Cortex, the regional downscaling models across all regions of the world, and it allows you to interface with all of these data sets, to look at global maps of these, to look at information over particular regions. So the main view that you're seeing, which is represented in the top left of the figure here, is what you see when you come to the Interactive Atlas regional information component, and then on that you can select different options in terms of the variable, the index that you're interested in, the time period, the scenario, whether you want observations or whether you're looking at projected changes, the season that you're interested in, for example, and also you can select the region or the set of regions you're interested in. And if you select a region or a group of regions, you will then get summary statistics will be that you can then explore, such as time series, such as the change in a particular CID at certain warming levels. So that is an example shown in panel D of this figure. You can look at the evolution of the CID in a projection across all of the models using stripes. So that's the panel B you've got there. You can do scatter plots to compare changes in temperature versus precipitation, for example, look at changes in the seasonal cycle, and there's also a table function which allows you to look at the average change and the spread of changes for a particular region or set of regions. So that is that's a whistle-stop tour of the information that we have in both the main report, summary information on regional information, and the interactive atlas. So just in summary, something that is new in this report is a very significant focus on regional information, and specifically it's relevant to impacts and risks. So this includes this new concept of climatic impact drivers, which is relevant to the Working Group 2 assessment, but obviously also to society and ecosystems more generally. A very clear articulation of the assessment process we went through to generate these findings on regional climate change. The bringing together of all of this evidence, it demonstrates very clearly that multiple and diverse sets of changes are and will increasingly be experienced in all regions. And finally, as part of this effort, we have developed this innovative online tool, the Interactive Atlas, which explores which allows you to explore the summary findings with the regional synthesis and also the observational and projection evidence that underpins those. And just one final word on that, the interactive atlas itself is available for the IPCC website, but at the moment it is only the regional information component that you can explore. The regional synthesis is still being finalised because it links very closely with the SPM, which itself has just been approved, and that is going to be launched at an event in about a week and a half's time in Spain, and then it will be available from the end of the month. So thank you very much for your attention and looking forward to questions later.
Thank you very much, Richard. That was great, and also good to hear about the forthcoming release of the other component of the Interactive Atlas, which I've had a chance to look at in the kind of revision stage, and it's definitely a good tool for people to use. So if you could unshare your slides, and we'll move on to our final speaker of the pre-lunch session. So I'm very pleased to welcome Tamsin Edwards from King's College London. So Tamsin was a lead author for Chapter 9 on oceans, cryosphere and sea level. But today she's going to focus on the sea level rise part of it. So whenever you're ready, Tamsin, over to you.
Thank you very much, and yeah, thanks to everyone who's come and stayed with us today in this meeting. Yeah, so oceans and cryosphere obviously relevant to sea level change, so I will mention a little bit about all of them. I'll just recap first of all some of the things that Peter said in the first science talk. You know, one of the key messages I think of AR6 was you know, some of the things we've heard a lot about already: climate affecting every part of the world, the human influence, and the unprecedented nature of the changes. So in terms of unprecedented for this part of the report, glacier retreat is unprecedented since the 1950s, with almost all glaciers retreating globally in at least 2,000 years, and sea level rise has been faster since 1900. Than any other century in the last 3,000 years. That's been about 20 centimetres of sea level rise, but particularly important is the fact that the rate has nearly tripled during that time. Peter showed the numbers in his talk slides. In the past 50 years, that sea level rise has been about half due to the expansion of the oceans as they warm, which is not a particularly well-known source of sea level rise, I think, in the public necessarily. About just over 40% from the glaciers and ice sheets, and the last little bit from changes in land water going into the ocean as well. As I mentioned, human influence being the main driver, not just of global mean temperature changes, but many aspects of climate change.
Tamsin, can I interrupt you a minute?
Sure.
We're asking if you have meant to share your slides yet, or whether you were.
Oh, am I not sharing? I'm so sorry.
No problem.
I thought I had clicked it, but clearly not. Click again. Try share content. I'm so sorry.
No
I was encouraging my students to pipe up, so thank you for doing that. Yeah, so this was the simple graphic on the first slide, a cartoon of some glaciers and sea level rise. Thank you. The human influence that I was just going to come on to, it's virtually certain that not only has the upper ocean warmed since the 1970s, but extremely likely that human influence is the main driver of that warming. The glaciers since the 1990s, human influence again, the main driver. That's a very likely assessment. Sea level rise also very likely the main driver since at least 1971. For the ice sheets, Greenland, it's very likely that human influence has contributed to the surface melting that we've seen over the past couple of decades. And for Antarctica, it's limited evidence of human influence. It's a more complex ice sheet, I would say, than Greenland. And you know, in this report, as in all, I suppose, the one of the most sort of standout aspects for me, and I'm perhaps biased because I work on ice sheets and sea level rise, is the irreversible nature of some of these changes. So there is a statement that many changes due to past and future greenhouse gas emissions are irreversible on centuries to millennial timescales. And of course that particularly applies to the oceans, ice sheets and sea level rise. So past greenhouse gases have committed the global oceans to future warming, again, irreversible on sort of timescales of centuries to thousands of years. For Greenland, it's virtually certain that there'll be continued ice loss this century, so that ice loss has obviously been contributing to that increase in sea level rise in recent years, in recent decades, and that will continue this century. The world's glaciers, the mountain and the polar glaciers, are committed to continue melting for decades or centuries. Now, some of that loss might be irreversible on long time scales, but essentially we are committed already, even with current warming levels, to continue melting there. For Antarctica, again, a bit more complex. The assessment is that it's likely to continue losing ice this century. That's essentially because in a warmer climate that can hold more moisture in the air, you can get more snowfall, and of course where it's very cold, like Antarctica, the moisture will fall as snow and build up the ice sheet in the interior, the cold interior. And that's particularly true for Antarctica. It's a bit true for Greenland, but the snowfall increase in a warmer climate, we think, can partially offset some of the losses of the ice, which are more due to things like ocean changes. So that adds up to basically sea level rise being virtually certain to increase in the 21st century, and that it's committed to keep rising for centuries to millennia, to remain elevated for thousands of years. As I said, some changes could be slowed and some could be stopped by limiting warming. Of course, the different emission scenarios that we've heard about from particularly Amanda and Yuri will make a difference to these changes, and some changes could be slowed or possibly reversed in the long term. I want to spend a bit of time unpacking two panels from a figure in the summary for policymakers. So this is the panel D of SPM 8, and it shows the global mean sea level change relative to 1900 from 1950 to 2100. So of course in the past up to today we've got observations of that sea level change. The scale there is in meters. And then we've got the main part of the graph is showing the 5 different shared socioeconomic pathways that we've heard about, ranging from SSP 119 at the low end, the very low emission scenario, through to SSP 585, the very high. And the shading here is shown for the second lowest and the second highest of those. And that shows the likely ranges of those projections. Now, before I kind of go into the numbers and the dash line here, I want to just add that we really do have a sort of a step change in assessing sea level rise in this assessment report. As we've heard for equilibrium climate sensitivity, for the global mean temperature projections, for the ocean heat content, we've been using these simple climate models to make the assessment much more thorough and comprehensive and much more consistent across different aspects of climate change. And that feeds into these sea level rise components as well. So we don't have a single sea level model. We don't have a single sea level rise output from global climate models. We have to put that together from many different components. We have many different models making predictions for Greenland, many different models making predictions for Antarctica, many for the world's glaciers, and then we have the ocean expansion that I mentioned, and other bits and bobs as well. And all of those have been linked within the same emulation framework, so that the global mean temperature projections in the rest of the report are used directly in these sea level rise projections, even though we've kind of done that, if you like, after the fact. We've used simple climate models and statistical models to represent the way each of the components of sea level rise responds to global mean temperature, So we've driven those different components with the same global mean temperature projections as the rest of the report. So that's very different to previous reports where we've been constrained to using the literature, which often has to use previous emission scenarios, previous generation climate models, and so on, because of the extra time that it takes to make these different ice sheet and glacier projections and so on from the global models that were produced. So the global simulations. So it's a much more consistent picture. There's also been extraordinary work done by Bob Kopp and Greg Garner on lots of sensitivity testing, trying lots of different components for each of these contributions, multiple different sort of assessments of the literature and treatments of simulations and extrapolations. There's incredible complexity in chapter 9, I would say. So sort of coming back to the actual numbers, the shading here for the SSP 126 shows a likely range of around 50 to 80 centimetres, and the shading here for SSP 370, which we heard was a little higher than we're currently tracking at the moment, goes up to about 1.1 metres. Those are both since 1900. Now, you know, these tens of centimetres don't sound like very much, but if you look at the top of chapter 9, you can see that extreme sea level events that would in recent years happen once per century are predicted to become 20 to 30 times more frequent by 2050. That's across the sort of most of those scenarios, all but the lowest. And in 2100, predicted to become 160 to 530 times more frequent. So the lower end of that range, as I say, is SSP 126, and the higher is SSP 585. So some extraordinary impacts on, you know, coastal flood risk around the world. I think there's a question in the chat I can quickly answer. Those are under assumptions just of the increase, basically, of the global mean sea level rise, the impact on those coastal flood events. It doesn't include changes in storm surges and some of the other factors that can affect those flood risk events. So those are the kind of main projections. The dashed line here, again, is trying to really encompass and incorporate aspects of risk and uncertainty that we know are important to decision makers. So we have we've heard already about low likelihood, high impact outcomes. So those are outcomes for which the probability is low or else unknown. It's perhaps deeply uncertain, as we'd say, but the potential impacts could be high. And so in this case, the dashed line shows the 83rd percentile of the potential impact of deeply uncertain ice sheet processes. So ice sheet instabilities, particularly for Antarctica, are part of that, but also increased response for Greenland. And if you're familiar with the literature, those are essentially coming from expert elicitation, although they also encompass the recent projections for marine ice cliff instability for Antarctica, the mechanism of rapid ice loss, which was published this year by Rob DeConto and others. So that dashed line is the expression of this kind of potential impact of deeply uncertain ice sheet processes in the 21st century, which in the summary for policymakers is described as approaching 2 meters. It's about 1.8 there for the 83rd percentile. And just the last figure I want to show, and it is a bit zoomed out because unfortunately the scale goes very high. This is now taking, we have got panel D at the bottom, which I just went through for the 21st century, but we also now have on the same scale the projections for 2300. And it's just shown for the second to lowest scenario, SSP 126, and the very high emission scenario, SSP 585, effectively because there's a lot less literature going beyond 2100. And so we restricted ourselves to those for which there was the most information. The shading here is showing, it's not an assessed likely range, it's simply the 17th to 83rd percentile ranges of literature effectively that's come out since AR5. along with some additional estimates we made within the AR6 chapter, things like extrapolations of other studies beyond 2100 under different assumptions. That's all kind of, as I say, laid out in multiple tables in chapter 9. And so since 1900, the bottom of the lower of those two emission scenarios shows 0.5 to 3.1 meters since 1900, and the higher is 1.9 to 7 meters approximately. And that is showing, as I say, the main kind of range of the literature. The dashed arrow above the very high emission scenario shows again a sort of another low likelihood high impact outcome. So again, this idea of marine ice cliff instability, a proposed mechanism of rapid ice loss from Antarctica, where the edges of the ice sheet sort of collapse very rapidly into the oceans and sort of in a very self-sustaining way. That is showing that the 83rd percentile of those recent projections that came out this year that we cannot rule out actually exceed 15 meters of sea level rise. The scale here only goes to about 10. So the paper is around 16.5 meters, in fact, for the 83rd percentile. Now, we've shown that just as a thin dashed line because very much that's limited evidence. It's really based on one paper going up that high. So one model, one representation of this hypothesized process. But we felt because we couldn't rule it out, we've shown it in this way. So that is, I think, all I was going to say. And I'll just thank you very much for inviting me to speak.
Thanks, Tamsin. It's been a very intense morning of talks. It was very nice to end on such a calm and clearly presented talk. So thank you for that. What a great set of talks overall. Thanks to the speakers for keeping to time, which makes my job as chair much easier as well. So thanks from me and from the audience. And we're going to move on to questions. So I see that Yuri and Richard have come back on the microphone. So please put your questions in the chat as usual. And I'll try and get through as many as I can in the next 15 minutes. So we've got some questions already from earlier in the chat. Let's just see if I can find those. Yeah, so the question here from Philip Malpanis for Yuri. You refer to net zero, but some climate campaigners say this isn't enough. We need actual zero. Is net zero sufficient?
Yeah, it's a good question and a question I get very often. Let's first make sure that actual zero is net zero. No, is a more stricter interpretation of net zero. If you reach actual zero emissions, then you have also reached net zero emissions. So the geophysical requirement for halting warming is indeed met by these real zero or absolute zero demands. I think what one needs to take into account is that the evidence we provide here is the geophysical evidence, what we geophysically need to do to halt global warming. Besides geophysical evidence, when deciding for policies or for positions, you also take into account other evidence. And for example, there were several reports over the past couple of years, the special report on 1.5, the special report on climate change and land, that show the important trade-offs, side effects of considering carbon dioxide removal at very large scale. And if you combine these two pieces of information, then you can come to a position where you want to limit the amount of carbon dioxide removal being used to as low levels as possible. That last consideration is not a geophysical consideration, so it's not something that is assessed in Working Group 1, but clearly can underpin a call for absolute zero. So that's basically net zero with as little carbon dioxide removal as possible.
Thank you, Yuri. Okay, we've got a question now for Richard from Unknown. In the climate impact drivers for coastal ocean section, are the changes, if there are any, of waves included in the coastal flood and erosion components? It's quite a tough question, hopefully.
Yeah, so I can't answer in detail because this is work from chapter 12 that I wasn't directly involved in, but just to say that those findings are, all of the findings in terms of the CID changes are based on a very wide range of literature. And I do know from the coastal impacts literature that a lot of that involves modelling, which includes which includes representations of wave and surge processes. So those will certainly be included in some of the papers that we used in the underlying assessment.
Can I just add to that? Sorry, I did say it in the talk, but perhaps a bit quickly, that in the chapter 9 sort of executive summary at the top of the chapter, at least the numbers that I was talking about, the factoring of the extreme sea level rise, extreme sea level events, that was under the assumption, I'm quoting here, under the assumption that other contributors to extreme sea levels remain constant, for example, stationary tides, storm surge and wave climates. So I would say that at least those main kind of tide gauge, location estimates of extreme sea level are under without those extra components, even if some of the literature does, as you say, Richard, have some of those. Thanks.
Great. Thanks for that clarification. That's good. Back to Yuri. So this may be a difficult one for you to answer, but I'll ask it anyway. How does the carbon budget translate into national and household level carbon budgets?
Yeah, no, it's a good question. The IPCC obviously gives these budgets at a global level, because that's, again, the geophysical constraint, the geophysical limits for limiting warming to 1.5. Translating these, and as I highlighted already for these global level numbers, there are several normative choices that you need to make. The level of warming, the probability, how much non-CO2. When you translate this, want to translate this to national budget, company budget, household budget, there is a whole additional set of normative choices that you first need to make before you can actually quantify it. And for example, these are questions about ethics and fairness. How do you split up the remaining carbon budget over which time horizon? Which system boundaries do you consider? Is a national budget, does it consider aviation emissions of flights? Does it consider imported emissions? Does it consider consumption emissions? Again, once you have made those normative decisions, you can quantify them, not something that Working Group 1 or the IPCC is doing. Yeah, so that clearly, I think it's a good point to end to highlight that there is still a very big step to make between the geophysically determined carbon budgets that we report in the IPCC and then how they are applied in policy. So it's not just plug and play. It's really more input and information for a wider societal conversation.
Great. Okay. We've got a technical question again for Richard. Are the tools used to produce the figures, for example, the sectional hexagon plots? This might be a wider question about the availability of the software behind the atlas.
Yeah, okay, thanks for that question. So the simple answer is yes. The more complicated answer is that all of the software that's used to generate the interactive atlas and the processing of the data, the 5 season observational data underpinning it, this is all being done by at the Institute of one of my co-CLAs in Santander in Spain. I also should say that there's been a very significant amount of support from the Spanish government as a contribution to IPCC for the work that Jose, my co-CLA, and his team have done on the interactive atlas, which has been really very impressive. And for the really technically minded of you, the code base for all of that is R, and all of these all of the data and the software that is used to generate all of the figures and the results in the interactive atlas is sitting on a GitHub, which is openly available to those people who would who would like to explore it further. So you can get access to all of the underlying code if you would like to do so. And so, yes, so essentially all of the information, it's very traceable. A very important part of the work that we were doing on this was to make everything as open as possible, so that all of the results that you are seeing could be reproduced, are traceable, are transparent. And so if you look in the help information on the Interactive Atlas website, you will get links to all of that underlying code, or you can find those. And there are more details on all of this in the description of the Interactive Atlas within the Atlas chapter in the report.
Thanks for that comprehensive answer. And I think the same applies to all the figures in the SPM as well. I think you can get the code and data for those as well. We have a question from Stefan Singer for Tamsin. The dotted worrying curve under sea level rise is valid for the 8.5 scenario. How would a dotted scenario, a low likelihood, high impact scenario, look for the lower emissions scenarios? It's important for adaptation planning.
Yeah, there was a lot of discussion around whether and how to include more information in these figures, obviously. Effectively, the simple answer is that the low scenario isn't very different, and that's effectively what's not shown. The more complex answer is going into a bit more detail. The expert elicitation is a little higher than the likely range. Again, that's all kind of laid out in the table, in various tables in chapter 9. But the marine ice cliff instability is within the likely range, because the marine ice cliff instability is extremely sensitive to the emissions scenario. So it tends to kick in the kind of medium to high, and certainly in the very high emission scenarios. So that's where it really makes the difference. So partly a bit for simplicity of visualization, but mainly because it didn't make very much difference. That's why we only showed for the very high, rather than, for example, for SSP 126. Okay,
so it's low probability, but under a low emissions pathway, the probability is reduced even more.
Exactly, yeah, it makes much less difference. Yeah.
Great, okay, that's good. Somewhat random order now, sorry. We have a question for Yuri. While the multi-model mean may suggest that the warming commitment after zero emissions is zero, the individual models show really different behaviours. How confident are you that it's really zero? What do we need to study to constrain this better? That's from Steve Smith.
Yeah, thanks. These confidence of, fortunately, the IPCC explicitly looks and determines the confidence of its statements. So for the zero emission commitment, we determined that it is for a carbon budget of around that leads to 2 degrees of warming. The zero emission commitment is likely smaller than 0.3, so likely smaller than 15% of the total warming. But there is low confidence because there are few studies and there is different and the evidence is pointing in different directions about the sign of this zero emission commitment, and this is for 50 years after having stopped emitting. So that is what is currently out there. The literature is quite inconclusive about the actual drivers. They seem to be kind of not strongly correlated to climate sensitivity, because ultimately it is an interplay between climate sensitivity and carbon uptake.
Yuri, so question now for Richard from unknown user. Could Richard discuss the handling of model biases in constructing the atlas?
Okay, thank you. It's quite general. I'll answer something about biases. Hopefully, this will respond to the question adequately. So, one aspect of biases that we have addressed is that when we're generating some of the indices, some of the climatic impact drivers, which involve a physical threshold, like temperatures above a certain high temperature level. 35 degrees is one of the options we have. We do a bias adjustment on the results from the models, and so we present the changes in that index both as raw model output, but also as model output when bias adjusted using techniques which have been used in the Working Group 2 report to look at impacts, because they make a significant application of bias adjustment when doing impact studies. So that's one area of bias, treatment of biases. The other is that the outputs from all of the models that are represented in the interactive atlas, you can look at them as raw outputs, as the absolute values as well as changes. We have the ability to split the screen on the interactive atlas, so you can view the observations on one side of it, and then you can view what is being generated by the models on the other side. And then in the time series, what you will see is, again, you can see time series of observations versus what's going on in the model. So that allows you to get a handle on the biases in the model. So, so there is a treatment of biases in terms of bias adjustment for some of the indices, but we allow exploration of the biases by the different options within the interactive atlas.
Thanks, Richard. Question from Richard Wood for Tamsin. You mentioned the large changes in 100-year return sea level streams. Can you make any robust statements about 1,000-year return period?
Yeah, I just checked the chapter, and I'm pretty sure we only give the 1%, not the 0.1%. And I think, you know, given the rather large uncertainties, the deep uncertainty in the ice sheet processes, particularly under high emissions, I think that would be behind that decision.
Plenty of space for more research. People can apply the IPCC assessment and apply it to their own location, perhaps with appropriate models. And
yes, I think, you know, the statistical details, the distributions and parameters and things, a lot of that is in the supplementary as well, so people can look at that if they want.
Okay, thank you. Back to Yuri. How realistic is, sorry, this is from Alex Zeffert. How realistic are negative emissions of 10 gigatons per year by 2100 as shown in SSP 1.9?
Yeah, so the technological solutions and mitigation measures are not assessed by Working Group 1. So this is really something that will be looked at in Working Group 3 that will come out next year as well. And any questions of realism in terms of policy, a lot depends on the actions that we undertake now in the next decades and which policies we put in place to get to somewhere by the end of the century. So even if there is a technical potential to reach these levels, without the right policies, they will still never happen. So, but I would recommend to keep an eye out for the Working Group 3 report that will come out early next year.
Thank you. Okay, we've got lots more exciting questions in the chat. We're short of time to go through them, I'm afraid. I've got to start summing up now before we have a lunch break. It may be that some of those questions are relevant also to the afternoon panel discussions, so you may have a chance to ask questions like that or similar ones later on. So I'll keep this brief because I'm sure we want to have lunch. But first of all, thank you to all our speakers for the time and effort they put into making their marvelous presentations. Thanks also to our audience for your stimulating questions. I'll just say a couple more things before we break. You might have noticed when I introduced the speakers that I stated their IPCC authorships in the past tense, because the production for the Working Group 1 at least, the production of the 6th assessment report is almost complete. So I'm sure our speakers are looking forward to a break from their IPCC commitments, unless of course they volunteered for other working groups or for the synthesis reports, which will continue through the next calendar year. I think we should also express our gratitude to the speakers for their contributions to this IPCC assessment process, which is essentially on a voluntary basis, and yet the assessment itself, so important for providing scientific baseline for the global climate policy process. So thank you all for your contributions to the IPCC as well. I've got a minute or so to share a couple of my own thoughts about the IPCC 6th Assessment Report. One is to remind people of a particular strength is the concept, which I think people call the line of sight concept, which means there's a clear line of sight or set of cross-references from every statement or conclusion in the summary for policymakers, back to the technical summary for details of the assessment, or back to the particular chapter subsections where the assessment is made. I think that's a real strength, because it means that what you see in the SPM is not just simply a statement or a claim, that you can actually follow through to find the evidential basis for that statement. And I think the other thing to point out is that sometimes you get the impression that the physical science basis of climate change is so well established that people aren't expecting the Working Group 1 reports to be very exciting. But that's not true at all. There's so much science going on and so much new things we learn each time, and the assessment reports do such a good job of bringing together that assessment. The narrow assessment of climate sensitivity is one that stands out, but there's so many others as well.